Welcome to Physics Made Easy channel. Today's topic is transistor as an oscillator. We had an introduction of this topic in the last session, and now we shall first revisit it and then we will proceed ahead. An oscillator is an electronic circuit which produces electric oscillations of constant frequency and amplitude. Remember this thing, frequency is constant and amplitude is constant. Now it converts DC energy obtained from battery into some AC energy or into oscillatory energy. This is the graph that we will discuss, and this oscillatory energy will be clear from there. Or in plain language, it converts DC to AC, DC current, direct current to alternating current. Principle of an oscillator, it is based on the principle of self-sustained transistor amplifier. The term self-sustained is very much important. We don't give it any input. Initial energy is given, then some part of the output is fed back. Self-sustained transistor amplifier with positive feedback. This is basically the transistors. LC oscillations are fed into it. For example, this is the LC circuit and this is transistor amplifier, and here we get the output and we feed back some part of the output to the input. Again, essential part of the circuit is LC circuit, transistor, and then you can say the feedback circuit, which normally consists of a resistance. Basic part of an oscillator. Tank circuit is a basic oscillatory circuit in which inductance L, this is inductance L, and this is capacitor C. They are the essential part. There may be some additional component as well, but these two are the essential parts and they are used in parallel. And tank circuit is just the parallel combination, as I have just said, parallel combination of inductor and capacitor. And the frequency of oscillator is given by nu is equal to 1 by 2 pi into under root of LC. But why do we need amplifier? If we can just get oscillations out of an LC circuit, then why do we need amplifier? We need amplifier because the oscillations are damped due to resistive loss. Oscillations, now current flows through the wire. These are the wire. When current flows through the wire, then following the Joule's heating formula, some part of the current is lost in the form of heat. And there may also be dielectric losses as well. And even inductance is having some resistance. Now, keeping these things in mind, there is loss of energy, and as a result, the oscillations are damped like this. Their amplitude, for example, the amplitude of voltage, it goes on decreasing like this, and ultimately these vibrations die out. Now, what is the role of this transistor amplifier? It just sustains these oscillations. It just sustains these oscillations. Some part of the output is fed back to the input. And the part fed back, this positive feedback, makes up for the loss of amplitude of the voltage. Now, it receives oscillations from the tank circuit, amplifies by the transistor action, and then fed back some part of this. Next is the feedback circuit. A part of the output power of the transistor amplifier is fed to the tank circuit in phase. This is given back to the tank circuit in phase to the input signal. Feedback enables oscillator to produce undamped oscillation. Damped oscillations are those in which the amplitude goes on decreasing. In this case, voltage, the amplitude of voltage goes on decreasing. Damped oscillation may be mechanical or electrical, but here we are concerned only with the electrical oscillation. And here this voltage, the amplitude of voltage goes on decreasing. And to make up for it, what we do, we just uh, use an amplifier. Amplifier amplifies the output and then gives a part of this output back to the circuit. And this positive feedback, which gives the signal in phase with the LC oscillation, this positive feedback, it makes up for the loss due to damping. So damping losses are compensated by feedback circuit, and transistor circuit amplifies the input signal. Now, if I outline the roles of these three circuits, LC oscillation circuit produces oscillations, but they are damped one. These oscillations are fed to transistor amplifier. Transistor amplifier amplifies the oscillation. Then a part of this is fed back to LC oscillations. So in this way, we get undamped oscillation. And here I will show you, we won't go through this part. This is undamped oscillation. In this case, amplitude remains constant. And this is damped. In this case, amplitude goes on decreasing with time. And here we have just outlined how LC circuit produces oscillations. For example, initially we charge the capacitor and then we open this key and close this key. Then what happened? Initially whole of the energy is electrostatic, that is in the capacitor. Current starts flowing. Here half of the energy is electrical and half is magnetic. And after some time whole of the energy is magnetic and electrostatic energy is zero. And now this flux starts collapsing. When this flux collapses, then what happens? Magnetic energy falls and electrostatic energy grows. In this way, energy oscillates between the electric field and magnetic field, and it is responsible for producing oscillations. So ideally this kind of oscillations were expected, but actually this kind of oscillation, damped oscillations are there. And by making use of amplifier and positive feedback, we make these damped oscillations undamped. Now we will go to the original topic. Now, here we have got a circuit. There are various methods of feedback. One is coupling. Here we have got LC circuit. LC circuit is coupled with this circuit. LC circuit is coupled with this circuit. And the input of this circuit, this is LC tank circuit, which gives us the oscillation as an input. And here VBB is the biasing battery, which is responsible for keeping this transistor as forward biased during positive as well as negative half cycle of the wave. And now when the current rises, for example, when current rises, the output rises here. The output rises here. This is coupled with this, for example. This is coupled with this. So as some part of the output is fed back to the LC circuit through this inductive coupling. So what happens? This stops the input from falling, or this makes the input undamped. If the input is undamped, then output will be undamped. Now let me first describe you the circuit. Obviously here we have got LC oscillation and core is common. Note that this core is common. This core is common, and from here we got output from some other circuit, and this is through the core is coupled with this oscillator L1, and now inductor L1, and LC circuit now gets energy and oscillations are taking place inside the LC circuit. These oscillations are fed back as input to the transistor. This battery VBB is responsible for keeping emitter base junction forward bias during positive as well as negative half cycle of the input wave. Now, keep this thing in mind that from LC circuit we get oscillation like this. We get oscillation like this. So our responsibility of this VBB is this battery is to keep emitter base junction forward bias during positive as well as negative half cycle. Now here this is the VCC is the collector battery. Its basic responsibility is to keep the collector emitter junction reverse biased. And now when the current grows here, current grows here, inductor opposes the very growth of current. Now this opposition gets coupled with this. This opposition is once more opposed. You can say here positive thing was made negative by this L2, that negative was again made negative. Two negative makes one positive. So here this is an in-phase coupling. You can think in these ways. And now this is the second part of the circuit. It is again the same. I don't find much difference between the two circuits. Inductive coupling output. And now I will go through a tank circuit is made up of inductance L1 and variable capacitor C1. It is connected to forward bias emitter base junction. I have explained you all. And L2 is the feedback coil. Now working from 0 to saturation, this I want to explain. Now when the key K is closed, now this is the key K. When this key K is closed, you can say when this key K is closed, small collector current starts growing. Now collector current starts growing through the coil L2. The increase in magnetic flux linked to L2 and hence with the coil L1, because the core is same and they are close to each other, not far away. This induces EMF in coil L1 in direction forward biased, and a positive charge begins to build up in the upper plate of the capacitor C1. The forward bias increases the emitter current. As emitter current increases, it leads to collector current increase in IC, and now magnetic flux is equal to, we know that phi is equal to Li. Phi is proportional to I. As the current grows, magnetic flux grows. Phi is proportional to I, and this L is coefficient of inductance. Here he is using the formula. For example, if I show this in diagram, I will use this diagram. Now if current grows, we know this formula. We are simply familiar with this formula. Phi is equal to Li. Now from here, IC grows here. If IC grows, what does it means that phi 2, I will call it as phi 2. Magnetic flux linked with this is phi 2. Phi 2 grows. If phi 2 grows, then what happens? Magnetic flux linked with this circuit grows. Now growth is always opposed. This increase in the magnetic flux linked with L2 and hence L1, as a result forward bias increases. As a result forward bias increases, which further increases the emitter current, the collector current, and charging of capacitor continues. This process continues till the collector current reaches saturation. Now, remember the curve of collector current. Output characteristic, just keep in mind, irrespective of you can say configuration. So the graph is like this. After some time, it reaches plateau. Now, this cycle of increase in magnetic flux with L2 and then increase in input, it continues up to this point. It continues up to this point. Now, collector current reaches maxima here. IC is along this. Now, collector current reaches maxima here. This is IE. Collector current reaches maxima here, you can say. It reaches maxima. And now, once the collector current reaches maxima, then IC will not change. If IC is unchanged, inductor only opposes change in growth of current. Now if IC becomes constant, it means flux will die out and coupling will die out. If coupling will die out, then input bias will decrease. If input bias will decrease, then what will happen? At saturation, I will write here because I can refer easily to the diagram from here. I keep it. Saturation state. This circuit. From this I will explain. What happens? This is this saturation. At saturation, what happens? IC becomes constant. It means phi becomes constant. It means positive feedback stops for moment, not for always. Stops for moment. Stops. It means damping starts playing role. It means IE decreases. This implies input current decreases, IC decreases. Now there is a change in current. So at saturation, IC becomes constant, phi becomes constant, positive feedback momentarily stops, damping starts playing role, input current IE decreases, and as a result this IC decreases. Now if IC decreases, it means phi decreases, phi falls, and coupling again becomes active. And coupling here again becomes active. Because there is a change in flux and again positive feedback will be there. Now the momentary fall in IE will be compensated by this feedback. In this way, what happens? Amplitude of the output oscillation is always constant. Amplitude of the output oscillation is always constant. When the current through L2 stops changing, as I have said, the induced EMF linked to L1 vanishes, coupling stops, as I have used the word. The decrease in emitter current, IE falls. Here I have written IE falls. Then the collector current also falls. The decreasing current through L2 now phi falls. If phi falls, then coupling again starts. Because this opposes the fall in current, and now induced EMF will be produced and there will be coupling here. Hence collector current IC is also reduced. At the same time, positive charge. Now we have explained it all. We don't need to go through it. Now this is nu is equal to 1 by 2 pi into under root of LC is the formula for oscillation here. And positive feedback in common emitter amplifier, a signal applied to the base emitter circuit appears with a phase difference of 180 degree in the collector emitter circuit. The coupling of L1 and L2 also produces a difference of 180 degree due to mutual induction. As a result, energy fed back to the tank circuit is in phase with the input. Now this is very important point to be remembered. Now this L1 and L2 opposes a phase by inductive coupling inductive coupling induces a phase difference of 180, and the output in the common emitter amplifier is also out of phase. That is, there is a phase difference of 180. One phase difference of 180 is introduced by this transistor. Other phase difference of 180 is introduced by these inductors. So total phase difference is 180 plus 180, that is 360, means input and output are now in phase. So I will also write it here. Once more, it's an important point as far as understanding is concerned. And the point is, it induces a phase difference 180. I will write it here. Phase difference of 180 is induced by, you can say, 180 common emitter amplifier. 180-degree phase difference is produced by inductors. Total phase difference is 360-degree. 360-degree means they are in phase. 360 means both of them are in phase. So with these words, I finish this lecture, and in the next lecture, we will start the last chapter of electronics, that is digital circuits. Thank you very much.